Okay, today we go into chapter 5, kinematics of rigid body. So it will be part of your incoming test 2 and final exam area. Okay. I haven't finished marking. Yeah. Okay. First thing, when you look at rigid body, we look at how object move, how a rigid body move. There are 3 types of motion. First is called translation. So you have 2 types of translation. What I mean by translation? Okay. I take this marker pen as check. First motion on planar motion. First one, translation. This is called translation. Okay, this is called translation. The first one is rectilinear translation in straight line. Okay, this is rectilinear translation. Second one, curvilinear translation. Like a wiper. Look at the cap, the blue cap. Where is the blue cap moving? It's moved in a curvature motion. Okay, this one is rectilinear motion. Okay, this one link up with your experiment that you measure with L1, L2, L3, A1, A2, A3. Okay. So first type, translation. Translation, you have 2 types. One, rectilinear translation. You focus on the body and we look at 2 points. Previously, you only look at 1 point where it's particles. Now, when you enter into rigid body, you look at 2 points on the body, cap and the end of this marker pen, right? So this one, we draw the before and after. You see straight line is under rectilinear. You draw straight line, you draw the before and after, you draw the path between before and after, you see a curve, means is the rectilinear translation. Second type, rotation. Rotation is along fixed axis. So maybe this marker pen, you're able to see the word here. So it rotates at 1 axis. This is called rotation. So first one, translation. Second one, rotation. Third one is a mix between the first one and the second one, translation plus rotation. We call it general plane motion. There will be one question come out later, ask you to draw the outcome of general plane motion, right? Like this one. This one, before and after, is a combination of translation, means this point, translate to here, rotate. Okay, so this is the combination. So 3 types, translation, rotation, and general plane motion. There's no mix, but in this chapter, we use general plane motion. It means combination of the previous 2. Okay. So this is example of a body or rigid body that undergo the 2 type of motion. You focus on this wheel with the R radius. What happened? We are focusing on the link. This is called link. This is called link. So what happened? This point and this point. We are looking at 2 points on the rigid body. This point and this point. So when this point rotate, what happened to this point? This point is rotate. This point rotate down. This one, it will fix to a piston motion. It move in a linear motion. This side is translation. This is translation. This side, you link from this point to this point. When this one rotate anti-clockwise, this point move like a wiper. It move like a translation or collinear translation. Okay, so this object, this axis come up from the screen. Okay, this translate out. This object at the center is doing rotation. Object on the left, rectilinear translation. Object on the right, collinear translation. Okay. Then engineering, we like to link motion with equation. So we start with equation already. Yeah? So recall when you enter chapter 5, you only need to recall chapter 1, 2, 3, 4. Do some modification in the concept still same, but you need to do a little bit modification. When you do look at a rigid body, you have a fixed plane or primary plane where you observe from a certain point where x and y, and then the body where it's moving, we will use y prime or y comma and x comma. And then on the object itself, we'll look at 2 points. It's like your eyes and your mouth. You fix on the body. Okay? And then you will observe from your place, like my mouth and my eyes. What is the distance? What is the velocity? As I move forward, move backward, you do the calculation. What is the speed of my mouth compared to your location? Okay? So here, we try not to make things complicated. As you can see here, this is a vector diagram that you learn in chapter 1 and chapter 2. So from a fixed plane, location, how you pinpoint location? In this case, we use R rather than we use S because this is a tree. You can say this is in this case, the Z is same. So it's moving on the plane. So your position from the fixed plane, from the fixed position O to point A, we label as R sub A. From the fixed position to point B, we label as R sub B. And position position B relative to A, we write RB/A. RB/stroke A will be different from RA/B. Not same. Huh? From this chapter onwards, when you write your equation, relative position, you need to be careful. Huh? Because normally after chapter 5, this is the final answer we're looking for. Okay. Then, what vector equation you can write? Yeah, vector equation. What plus what's equal to what? RB? What's your answer? Again, repeat your answer. R equal RA plus Nico, correct or not? Huh? Again, repeat your answer.
We need to include I and J because it's vector form.
Why input R and J? From this diagram, how do you identify as I and J? Again, don't try to complicate yourself. There's no value for you to find I and J. How you find I and J? Since you raise it up, how you change RA into I and J? You tell me. How to change RA into I and J? Since you bring it up. Huh? But if you want to, if you need to find, how you find? How? Where's the cost? Where? How you find cost? How you split vector? How you split vector? From how you split vector? How you split this vector into I and J? Huh? Where is the angle? RA, go. RA. Then? You know? Since you bring it up, you need to recall how you split your R and J. When you split this one IJ, this one also IJ, this one also IJ. Then you group based on I, group based on J. Okay, there will be one question come out in your final exam. Okay, position, we use R, as what I told you. And there's a relative, which is B respect to A, you write R, B stroke A. So vector equation RB equal to RA plus RB stroke A. Okay, correct, huh? Just now the equation. So velocity, how you find velocity? The position, how you find velocity? Huh? V equal to ds dt. Is there any S here? V equal to dr dt. Take time derivative. dr v dt, you get vb. dr dt, you get va. dr b stroke a dt, you get this one. Okay. Just now I mentioned AB is like my eyes and nose, right? My eyes and my mouth, right? What happens if you dt the distance between my eyes and my mouth? Huh? Okay, y0. Not fixed. What's the distance between my eyes and my mouth? A and B. It's fixed, right? Constant, right? Constant, you do time derivation, what is the value? Huh? 0. There's no change of my length of A and B. My eyes and my mouth doesn't change, right? So you can cancel. So for rigid body, my any point that on my body will move in the same speed. And if you see as a one body or rigid body. Okay, this is a main difference between the previous chapter 1 until 4. When you go into chapter 5, you look at that body only. So in this case, we conclude that velocity of B will be same as velocity of A. Why? Because it's on a rigid body. It's on the same body. Okay, same with acceleration. How you get acceleration? You do this one, dv dt, you get acceleration. Same, All right. So any questions so far? Very easy, Okay, good. Now we start to use your right hand rules. Chapter 5 onwards, your right hand rules is very important. You should know where is the direction, come out or come in, or clockwise or anti-clockwise. So let's look at this blue body here and we'll focus on point P. This point P, when you rotate in the anti-clockwise direction, use your right hand rules. So this P on this rigid body, it move in a circle, right? Move in a circle, and we are using polar coordinate. Polar coordinate R is positive if you move from the center. R positive when you become bigger and bigger. R positive value go up. Then your angle in this case, right hand rules, angle will be anti-clockwise positive. So from reference point, rotate anti-clockwise, you get positive. Then you have a position R, you have a P, O, and if there's a change of angle, we use theta. Okay. Introduce you a new term in rigid body. We start to see the word angular. In particles, you see position, you use S, velocity, you use V, ds dt, acceleration, A dv dt equal to d s square dt square. If you freeze time, you get A, but ds equal to V dv. Okay. The final exam, this one come out. Okay. So, and then there are three motion equation that you derive. V1 equal to V O plus A T. Second one, V square equal to V O square plus 2 AS delta S. Delta S equal to T plus half A T square. Okay. When you look into angular body, you will repeat the same, but you look at the angular, what I mean by angular, rotational motion or translation motion. So angular motion, we will look at radial line R, what happened to that plane. We'll look at this plane. So angular motion is defined, position R is defined by angle theta, this theta, this one. Okay. So angular position of R is defined by theta. This R is defined by theta with reference of fixed reference line. This is fixed reference line. to R. First, we call it displacement, angular displacement. We use theta. In particles, we use S. In angular displacement, we use theta. And we no longer use position, we use displacement. Okay. And because of we are looking at rotation, you need to recall calculation in radian. Before that, in your circular, partial circular, there's a equation here, S equal to R theta. This is in radian. And in angular, you rotate one revolution, means one cycle. One cycle, how many degree? 360. 360 equal to 2 pi radian. Start from chapter 5, you start to use radian. Okay? So 2 pi radian equal to 1 revolution. You will start looking at question, tell you the object turn how many revolution. Okay, you look at the question, you see revolution, you know that is chapter 5 onwards. The question refers to chapter 5 and onwards. And it's under rigid body. But in rigid body, don't use particles equation anymore. Okay. Again, is defined by right-hand rules. In this case, particle R move anti-clockwise. You have all these terms. We will look at each one of them. So, if you look on the top, right? Look on the top, this one. Point P, rotate anti-clockwise. First, we introduce you displacement will become velocity. We start to use omega symbol. What is omega symbol? How do you find velocity? You take what? Position, time differentiation of your position, ds dt. But when it comes to angular, what do you take? Displacement and time derivation, d theta dt. You start to do some transformation on the symbol. Okay? And is anti-clockwise positive. Right hand rules. Okay, chapter 5 onwards, you start to look at your right hand. Okay. So angular velocity, d theta dt. After velocity, you will see acceleration. Acceleration, we use alpha. Alpha equal to time differentiation of your velocity, d omega dt, or d square d theta dt square. Makes sense. Okay. So velocity will be in radian per second. Acceleration will be in radian per second square. Particles, velocity will be in meter over second. Acceleration will be meter second square. Start to differentiate chapter 1 until chapter 4 and chapter 5 onwards. Chapter 5 onwards, you are looking at rigid body. You look at angular motion. Okay. This is what I write on the whiteboard. And if your angular velocity decreasing, you are having deceleration, angular deceleration. Okay, again, particles, you freeze time. Angular motion, you also freeze time. You will get alpha dt equal, sorry, not this one, huh? Okay. You rewrite the equation, for example. You pull the dt to the left-hand side, w down there. This one, you pull alpha dt equal to omega, right? So you substitute your dt equal to d theta d omega. You substitute inside here, you get alpha d theta d omega. Pull the omega to the left hand side, you arrive at alpha d theta equal to omega d omega. Do you see the same thing? What is changing? Only the symbol. Particles A become alpha, S become theta, V become omega, V become omega. Basically, you already know. We only need to change the concept. The concept system. You only need to change a bit on the parameter. Okay. Okay. Any questions so far? Makes sense, huh? All right. Now, when we have a constant acceleration, particles, constant acceleration, you have three motion equation. We are not going deep into derivation anymore because the derivation will be exactly the same as chapter 1. We will not go deep into there. We arrive at these three. First equation, particles V1 equal to VO plus AT. Change the V into omega. 1 equal to omega 0 plus A become alpha, time remain. Okay, second one, still same. Omega 1 square equal to omega 0 square plus 2. A become alpha. And what is S? S is your theta. Same with this one. S you change to theta equal omega t plus half alpha t square. Exactly the same pattern. Only one is angular dimension, use right hand rules, and the angle of rotation anti-clockwise become positive. Okay. And when you can use these three equations on the board, it must have what constant? Angular acceleration must be constant. So it is very important. There's a difference between acceleration and angular acceleration. There's a difference between velocity and angular velocity. In your answer, you don't give angular in velocity. Then, since these two, they have similar pattern, we will link this side to this side. Because normally you don't communicate with people in angular things. You don't communicate in radian per second. You communicate in how many meter per second, how many how many meter per second square and so on. So there's a conversion from angular to particle dimension. Okay. All right. Now, if you look at the diagram just now, we add in a little bit on the diagram, but it look complex, but actually you already know all this. You look at the diagram, this is circular motion. You look at point P. Point P is moved in circular motion. When you learn in chapter 3, you learn about collinear motion. What happened? What's the next steps when you have collinear motion? Tangent and normal. So you have tangent velocity, normal. Normal tangent. Normal normally we use for acceleration. Okay, normal inside tangent to the curve. Velocity always tangent, right? Then there's a reference point here. There's a theta that you learned just now on the plane, but there's another reference plane. Okay, so this is a fixed point, and then you find a one point on the body, and you measure the distance from that fixed point to the point P, which is give you RP, and there's angle. Okay. So when you look at the top, P, you have V and R. Okay. So motion of P and R, you're seeing vector here. All these are vector. There's a calculation there. So a small circle, that you know that small changes on the circle, you can write ds equal to r theta. Like this equation, s equal to r theta. Small changes of this one will be equal to small changes of your s. So mathematics, you write ds equal to r d theta. So this is a small changes of circle here on the red color see on the screen. So velocity is velocity. It's not angular velocity. Velocity v equal to ds dt. How you calculate in the circular motion? S convert to r d theta. Okay, s equal to r d theta. R fixed because this circle we move in the same circle. R fixed is like your eyes and your mouth. The distance fixed. So you move your r to outside. D theta dt. Recall back in angular motion. When you have d theta dt, what you get? Is your what? Omega, and is your what? Angular velocity. Makes sense. So your v equal to r omega, but it is because of right hand rules. We don't write r first, we write omega first because you're dealing with vector. So it's important, don't flip the sequence. In vector, A cross B will not same as B cross A. Remember, this one is in your vector chapter in the mathematics. So there's one conversion equation like right on the whiteboard or on the screen there. You want to move here between these two. B equal to omega r. Okay. When you write like this, it's a scalar, it's a magnitude of that vector. Vector, you have magnitude and direction. When you want to find the magnitude of the velocity, or we call it speed, equal to omega r. Yeah. So today you learn angular equation. There is what on the whiteboard on the right. There's one transformation equation that link omega and r to the normal velocity. This equation link you velocity and angular velocity and displacement. Okay. The rest you already know. V always tangent in the circular path. Magnitude and direction of V is a vector. So if you want to write in a vector form, you need to use cross products, which is V equal to omega cross RP. The sequence cannot flip. You always take omega cross RP. Okay. Omega cross to the R. It gives you direction of your V. Right rules. Omega, you look at the omega axis. Omega axis cross to R. It gives you V direction. Okay. So important, your coming assessment, test 2 and final exam. Remember to tell us where is the direction. Draw arrow in your final answer. Okay, just a reminder. Okay, how to do cross? Go to Canvas, go and see appendix inside there. Already show you how to do, all right? Again, reminder, omega cross RP will not same as R cross omega. Direction will be different. One this side, one that side. Yeah, we always take omega cross R. Okay. Okay, the rest is repeat the same thing. Now, this diagram is on the V. Now we look at acceleration. For particles, when you look at acceleration, see, for particles, your acceleration equal to, sorry, we are right in the red color. Acceleration, you have two components, right? AN, UN plus AT, UT, right? How to find normal acceleration? V square over rho. You know that this one is angular motion. There's an equation to find rho, right? What is AT? V dot or dV dt. Right. This side is particles. You now look at rigid body. So same. At point P, tangent direction, normal direction. Now normal pointing in. And to find resultant, you get to find your A. You already done this one in previous chapter. So this tell you what? Where is the out direction? Where's the positive out direction? Go out, positive, or go in, positive? R go up positive. Means R go up positive. You see the vector direction between acceleration normal component and the R is the opposite direction. So this is what I extract from here. Okay. So your acceleration in previous chapter, you know that acceleration at tangent equal to dv dt. Acceleration at normal equal to v squared over rho. This one you learned before, right? Now, you substitute what you learned just now. Rho in this case is your R. This one, rho is your R. What is your V just now? V equal to angular velocity and angular displacement, omega R. You substitute inside here, what you get? Okay. Alpha equal to omega T. So here, V equal to omega R. What is fixed? R is fixed. R is fixed. Okay. So you pull out your R, you get your alpha R. So when you do angular rigid body, AN, not AN, sorry, AT. AT will be alpha R. Look at AN. You summarize, what do you get? Omega square R. For angular acceleration, omega square R. Yeah. Don't mix up between particles and angular chapter or rigid body chapter. So I highlight on the blue color on the whiteboard here. Take note. Don't use the wrong equation. So here, AT, this one you know already. So if P increase means your tangent increase. If decrease means you get negative acceleration. Negative acceleration means it moves in the opposite direction already. So just need to be careful because sometimes the statement will tell you, but on the rigid body will slow down. The speed, not speed, velocity slow down means acceleration also slow down. So the arrow of your acceleration, angular acceleration or acceleration will flip to another side. Okay, so normal component, direction of AN will always towards center. So in this case, okay, so I just want to tell you that actually the direction of between the R and N is opposite direction. So A equal to dV dt, this one you know. What is V? V equal to omega R. You're actually using cross products or chain rules. You can see that, right? So I don't need to explain. So this is chain rules. So when you have chain rules, this one, d omega dt, what is omega? Velocity, right? Angular velocity, time, you get acceleration. Here also same. Okay, here. dr dp is what? Velocity. Okay, so velocity is what? Omega r. Yeah. So here you can get omega r, but it's a cross products. Yeah. Yeah. Then here and here, you arrive at omega square rp, and this one alpha r. Okay. So alpha t is what we derived just now. To find the tangent acceleration, you take alpha r or rp sine theta here. And for n equal to omega square r, just now we derived already. Okay. But right hand rules. Vp equal to omega cross r. An equal to omega vp. Okay, in normal direction, omega vp. Your an, in this case, if you look at an, if you look at the direction of r, you'll get negative. Right? Your r vector is negative. Your an and r is negative. Okay. So when you rewrite your equation, at equal to alpha cross r, but your an is negative. So don't confuse when you write angular acceleration equal to alpha cross r minus omega square r. There's a minus there, and this one in particles is positive, but it's angular, it becomes negative already. Okay. You know how to find magnitude. This is vector. Square this one, square root. You need to calculate this one, to find this one to find this one. How to find? Go to appendix and see. It's a cross products. Okay. Next, by applying what you learned just now, and look at the diagram, you have two gears. On the left-hand side, B, rotate clockwise. C, rotate anti-clockwise. You focus on the A and A prime. Okay. What is the A velocity vector. How you draw velocity vector for A? Going this one, you break this. Okay, these two contact like that, right? You break gear B and break gear C, you separate them. Then you look at A. A will go where? Huh? Clockwise, but you imagine you are A. What is the motion you have? Collinear, it move in a circle. Right? So collinear motion, what is the velocity that you have? Tangent. So tangent go where? Go up, go down. Go down. Okay. For A prime, sorry. A prime, go down, but it's in clockwise direction. Sorry, anti-clockwise direction. Right. So you break the two, and then you know that this is this is tangent. Velocity like that. Again, velocity always tangent, no normal. Velocity no normal one in circular motion. But velocity you can convert into normal, into acceleration. Okay, acceleration A, you have normal and tangent direction. Right? A, you have normal, point to the center, and tangent direction. Tangent direction same with V. You need to find square root of n, square root of t to find the resultant of A. So A pointing, for B, you're pointing to the left-hand side. For gear C, your A prime acceleration for A prime point will point to the right-hand side of the gear. Yeah, acceleration, different direction. Okay. Let's look at this example, then we call it a day. All right, now you have a chord here around a wheel with it initially at rest. So what you have? Initially at rest. Velocity, 0. Or you now look at angular rigid body. Your omega initial is 0. So here 0, 0, 0. Okay. This is sorry. This is should be theta, not u. Theta type error. So means this theta is 0 here before it start. If the force is applied to the cord is a force pulling, give it an acceleration A. You see, this is acceleration now in 40 meter per second square. This is rigid body. It gives A. So it actually I want you to find angular acceleration, right? Where t in second in function of time. Find the angular velocity of the wheel, which is omega. B, find angular position of line OP in radian, which is angular position means theta in radian. So you look at the diagram. What you have? R. Then angular velocity is what? Angular velocity is what? Omega. Omega is what? Theta dt. Then what do you have? Acceleration. So how you think? How you link left hand side and right hand side? How you link particles and angular? You look at the whiteboard. Blue color one. Velocity. Omega r. You need to find omega r, right? Omega, right? V equal to omega. You learned before acceleration. How you link acceleration and V? A equal to dv dt. You have A. You have V equation. So how? A equal to dv dt. Then how you find V? How you find V? This mathematics, the concept is there. A equal to dv dt. What you have? You have V. V is given. So A equal to dt equal to dv. What is the next step? Integrate. What t you have? Huh? Okay. So you got A. Substitute this one. 4t dt equal to v dv. Of course, there's a constant now, but you know it will stop at a certain time, right? So, okay. Then you have three equations to use here. You have the omega 0. You want to find this one. You have the alpha. You want to change acceleration into A. So part A. Okay, the rest you read. You know that acceleration given there is in tangent. Right? What is the equation for tangent? Alpha r. So alpha r equal to 4t. Now it's not testing your this one. You try to like think what information you have. Then you try to group all the information together. All right. So tangent you already have. So you group them together. You have the r is 0.2. So you have 4t. So you have alpha. Alpha is what? Angular acceleration. So angular acceleration, it asks you to find angular. Sorry. Here don't have, but you have the angular acceleration. 2t radian per second square. In what direction? Clockwise direction. That's the blue arrow. And you pull down, so it will rotate clockwise. So you know that alpha equal to d omega dt. You have this side. You have dt. So integrate. When you integrate, put in value 0 to t. You'll get omega equal to 10t square radian per second square clockwise. Makes sense? Yeah. So you have alpha, you have omega. Again, what is omega? Angular velocity definition. D theta dt. Move dt to left hand side. Integrate. You'll get theta equal to 10 divided by 3 t3 cube radian. This is in radian. You're now in rigid body. You're no longer in angle. Okay. So this question cannot use equation of constant angular because A is a function of time. So A is in function of time. Means acceleration not constant. You cannot use this one. Okay, take care. So this one sometimes it's a trap. Okay, so this is how you find. This is a derivation of equation. Do you think you can go one more? One more, okay. Right. No class, right? No class, huh? Okay, one more. So this is a motto. So motto, so in the photo, turn a wheel attached to blower contained within housing. If pulley A connect to motor begin to rotate from rest. So this motor wheel, so pulley A is given here, right? So it rotate at a constant angular acceleration. It gives you constant angular acceleration. Means these three equations can use. Right, 2 radian per second. So this one turn 2 radian per second square. Determine the magnitude of velocity and acceleration of point P of the wheel P after the pulley have turned 2 revolution. This one turn 2 revolution. Assume transition, belt do not slip on the pulley and wheel. So, it asks you to find what? Magnitude of velocity and acceleration of point P. It asks you to find what? Magnitude of velocity and acceleration. It do not tell you to find angular velocity and angular acceleration. That is not the final answer. Although in the process, you need to find angular velocity and angular acceleration. But the question wants you to find velocity and acceleration. We mean you need to convert the angular term into velocity, angular term into velocity, into acceleration. Okay. So angular motion, draw your free body diagram. Okay. So first, it's always same, the step always same one for chapter 5. Step 1, look at the question, change revolution into radian. Yeah. So it give you 2 revolution. How many radian? 2 revolution. How many radian? Not 4. 1 revolution. How many radian? 2 pi radian. So 2 revolution. How many radian? 4 pi radian. Okay. 4 pi radian. You convert lah. Right. 12.75. So A constant, you can use any equation of the angular motion. In this case, you can find angular velocity of pulley A, omega. You substitute value, right? Find omega A, 7 point something. Okay, chapter 5. After revolution, the question will always ask you find omega, alpha, theta. Okay, then there were 3 right hand rules. Find the direction of that thing. Right. So omega, then you need to communicate in the velocity terms. Rigid body just now, since I think the second slide or third slide, your A and B will have the same velocity. Right? Velocity, A transfer, same speed. The belt move in the same speed. So velocity of tangent at this small circle here, velocity at tangent will same as velocity at tangent of B. Same. Okay. So that's why you can link omega AR equal to omega BR. You substitute the value. A you know, omega you know, R you know, omega B you don't know. So only one left out, unknown. Rearrange, you get omega B. Once you find omega B, find acceleration. So here, change into V and A. Substitute. You have your alpha A, which is 2 radian per second. R you know, so you find your alpha B. Okay, so you have omega B, alpha B. Then you need to find for A. for this one. So for P, you go to P, you have VP this side, this direction. Then acceleration, n pointing in, P along with the velocity. Then there's a resultant of P you need to find later. Yeah. So chapter 5, we are looking at this diagram. The question will only mention free body diagram and kinematic diagram. So you draw this one. This is what we're looking for. Huh? All right. So VP, how you find? Omega R. You substitute value, you get VP. How to find AT? Alpha R. Substitute, get the value. How to find the N? Omega square R. Substitute, you get the value. But here, when you find, again, A, you find AN and AT, remember to go back to find resultant of A. How to find resultant? Square this one, square this one, square root. How to find angle? Tangent. Okay. So you find your AP, you're able to get into this one. Huh? All right. So what else? Huh? Okay, we stop at example 2.